Welcome everyone to this session. My name's John Taylor and I'm with Synopsys. Formerly I was with Empirus. This time last year I think I was presenting for Empirus, but we were acquired by Synopsys in December last year. And I'm going to pick up on a lot of themes I think we've heard throughout the talk this week, throughout the various sessions and keynotes this week. I'm going to start with an introduction to some of the industry trends, talk a little bit about software-first design and why that's becoming more relevant these days. Then I've got a couple of case studies that we've done with customers. First one's scaling to a large many-core system. The second looking at chiplets. And this is how we simulate these large complex systems and why we want to do that. And then I'll wrap up with some conclusions and we should have time for some Q&A at the end. I'm sure everyone's seen this graph on the right before. It's been used lots of times over the last few years. It's a couple of years old now, but the trend lines are clear. And what we're seeing is, more and more cores becoming used as single thread performance caps out, frequency caps out. And so people are looking to parallelize their workloads for performance, whether that's within an SoC or across chiplets. We see tape-out costs growing at smaller geometries, so it's more important to be right first time. And at the same time, the pace of innovation is growing, the market windows are smaller, and a faster time to market is needed. And increasingly, and this is the theme we've seen the last couple of days, software is a differentiator. Callista talked yesterday about workload-defined silicon, and I think we see this more and more with RISC-V, particularly with customization being supported. And simulation is going to be critical to using that successfully, allowing yourself to explore what's possible and coming up with successful solutions. So when I talk about software-first design, the idea is that you're analyzing your software first and designing your hardware for that, rather than the other way around, which historically has often been done. You have your hardware, you're kind of fixed with it, and you spend all your effort on optimizing the software. And actually, this also speaks to co-design, which again has been a common theme over the last few days, that it's actually software and hardware being developed together and optimized together. If you want to look at customization, it's faster and simpler to test with models first. It's much, much easier to add custom instructions into a model and do some profiling than to develop RTL, verify your RTL, and use that to prove whether those custom instructions are worthwhile. And if you use simulation to develop your software, you can accelerate your deployment as well. So I'll show the benefit of this, but it means that production software can be developed in parallel with the silicon. And having a digital twin, you can explore both instruction set architecture and system level design. You can work out which custom extensions to use, how to do your interprocessor communication, what arrangement of cores and clusters you have. The introspection also becomes really powerful as well. So that's useful during development, but it can also be useful if you have post-silicon problems. You have much more power to look at the state in your design, look at the registers, look at what's going on, look at instruction execution traces and so on. In a simulation environment, it's much easier to do that than when you're trying to do it on silicon. When we look at some of the things going on in industry, we see that a lot of software projects are late and a lot of time is spent on debug. And so having those virtual platforms, starting that software development early means you can deliver your software earlier and faster. And we can see that, particularly as you get into customizing at instruction set level, there's a nice iterative loop you can use where you can profile your algorithm, do the analysis, work out where the hotspots are, and then update your model, go around that loop again as many times as you need to optimize your design. So when I talk about, what's the benefit of doing virtual prototypes and shifting left software development, this is the typical development flow folk would have used. You start your SoC development, you get the RTL design complete, you maybe move it to an emulator which runs that much faster, you can start software development on the emulator, and then afterwards you do your software development and eventually you get to production deployment. But if you have a virtual platform and you start work early, you can accelerate all of that much earlier. So as soon as that virtual prototype can be available, almost as soon as the architecture spec's complete, you can start your application software development, maybe even on a different host, start your firmware and OS development, move your software development onto the target ISA, and all of that can be done earlier. So by the time you get to emulation and final verification, your production software is ready in time with your silicon. And one of the use cases I'll talk about we'll see the benefit of that and talk about some of the timescales and how much you can benefit. There's a lot going on this slide. I know I touched on this already, but actually having models gives you lots of benefits. On the right-hand side, when it comes to some of the analysis things you can do, I skipped on. You can do a lot of trace profiling, look at code coverage, things like memory monitors, and there's also an API that means you can add your own custom extensions into this. So if anyone went to Newt's talk from MIPS yesterday when he was talking about performance analysis, you could think about adding a STF trace generation extension into this so you can dump the trace format you need for your performance analysis as well. You also want a large library of components, so if you're perhaps building a chip rather than designing your own core, you can bring in components from lots of different vendors. And what you also need is this to scale performance-wise. So as your complexity goes up, your simulation performance doesn't fall off a cliff, and actually you can still simulate the amount of code you have in your system at a reasonable speed. So we'll go into talking about some of the case studies now. And the first one is scaling to a large many-core system for an AI system. And what you find is that there's a hierarchical scaling up of complexity here. So from on the left-hand side, you start with a processing element. And that's quite simple. It's got a couple of CPUs in it, one with vectors, one without. There are some custom instructions in there. And that's a relatively simple system to simulate and build a model of. But that's built up into a larger accelerator, which has an array of these processing elements. You're now looking at trading off what your memory structures are, so how much is local to each core, how much is on the chip, maybe some external memory as well. You've probably got a management CPU in there to do workload distribution, and your complexity now has gone up from a couple of CPUs to tens of CPUs. In turn, those accelerators are put into boards where each board has a pair of accelerators on it, and in turn, those boards are put into chassis to build the final system. And you've now gone from only having a couple of CPUs to having thousands of CPUs. And at the same time, you want to prove your software architecture is going to work and scale across this, that you can distribute your workload as you want, and that the software stack is going to work. So when I talked about the benefits of profiling, if you're starting silicon, you can't get to building that system. You can't test it until you've got silicon and you've committed a lot in terms of development cost. Whereas with models, you can prove this out very, very early. So you can look at your hotspots in the code. You can look at which instructions are most valuable. If you're doing things like OS porting with something like Linux, you can get a lot of trace information even before things like consoles are ready. So if you're trying to understand why your OS won't boot, using a model can give you a lot of help trying to debug that. The parallel side of that is also for the compiler. So if you want to do toolchain development, again, you've added some custom instructions. Can you get the compiler to automatically target them, or are you going to have to do some inline assembly? If you're using vectors, can it auto-vectorize efficiently your code, or do you need to do intrinsics? And you can also look at things like trading off code size and speed, and trading off memory sizes. And so if you develop and test the software on the model, you can get all of this sorted out before you go all the way through with RTL design. When we think about that scaling to system level, often you are doing some sort of level of customization within the software stack. You might also be looking at trade-offs like, do I want more single-thread performance, or can I parallelize this workload? And we see on the right-hand side here that actually, you might start at a very high level with your user application, and maybe that's agnostic as to what host it's running on. But as you move down closer and closer to the hardware, you need a much more accurate model that has all of the architectural features in it. So you can even do things like device firmware development in a simulation environment. You can prove all your peripheral drivers. You can prove out all of the interprocessor communication. And again, because you've got that extension interface, if you need custom extensions within the simulator to help you with this analysis, it's possible to do that. And in this case, we had production software, or the customer had production software running on their silicon within a week of it being available because they'd done all of that software development in advance on a simulated system. And that's even on that deployed large chassis with those thousands of CPUs in it. The second case study, it's not dissimilar in some ways. Again, it's a scale-up problem. In this case, it's looking at chiplets and scaling to large SoCs. So rather than necessarily the customization being in the CPU itself, this time it's making decisions about, how many cores in a cluster, how many clusters in a chiplet, but also perhaps sourcing IP from different vendors as well. And that comes back to having that library of components and composability and ease of integrating components from different sources to allow you to build an efficient and high-performance simulation environment. And again, we see, there are still going to be hundreds probably of CPUs in that final SoC, but having that library of models makes construction of a complex SoC model straightforward. Again, we see that simulation performance, it's important that it scales linearly with a number of cores. So if you have poor scaling as you go from maybe 1 to 10 cores rather than getting the same total MIPS in the simulation, you get perhaps half that because there's lots of time spent context switching within the model. You can't possibly scale up to those hundreds or thousands of cores. Having the ability to add custom instructions is great if you want to do ML acceleration, and having that that customization in the model means you can build all of your software stack. And then we see SoC designers wanting to explore that partitioning. Where do I have smaller SMP arrangements and more clusters? Do I have more within a cluster? How big does my chiplet want to be if you're thinking about things like yield further down the line? And you need that modeling environment to be able to mix and match, pull all these things together, add your peripherals in as well. And ideally, you want all of these models to be available before that IP is final, so you can do your system exploration really early on. So bringing it all together, excuse me, system complexity continues to grow. As I say, we've talked about workload-defined silicon. We've talked about software, hardware, co-design, application-specific processors. And RISC-V does give you that freedom to innovate. It lets you customize the ISA so you can add in those custom extensions you need for your application. It also scales the profile so you can have portable software between systems. Having a well-defined customizable model allows you to do this iterative approach, building the analysis tools you need as well, and having that ability to introspect the design and look very closely at what's actually going on within the CPU core. And you can then optimize your system architecture. You can look at things like performance, memory size, interconnect, and things like that. The models, the Empirus fast processor models, are designed with open standard APIs, so you can easily add customizations to that. They're non-intrusive, they don't affect the model, but you can add, whether it's custom instructions themselves or whether it's more analysis and trace tools, OS-aware tools, and so on. And that early software development does mean you can achieve much faster product deployment. But it all builds from having that reliable, fast golden reference model. And we see this hierarchical building of core models, building subsystem models, building SoC models. So with that, I'd like to say thank you very much. We do have a booth through in the hall. I think there's some time now for questions, but if you want to follow up afterwards with anything, I'm also available there. Thank you.
Questions?
Behind you.
My name is Patricia. I'm from Berkeley National Lab. You showed in one of your slides where you could model IP from different vendors in a chiplet platform.
Yeah.
What do you think is needed to make that a reality? Right now, when you work in chiplets, like every vendor had their own process and their own system, and they only use their own IP. But the modularity of using IP from different vendors is very powerful. What do we need to make that happen?
So I can't talk to that in terms of things like physical connectivity and so on. What I would say is, certainly within the RISC-V community, we're working with most IP vendors already, so we have models of their cores. So in terms of being able to construct a simulation environment, I think most of that is there already. And as I showed with one of the case studies, we're doing that today with some of the customers we're working with. But it does mean you do need that library of models from the different vendors to be able to do it. One at the front.
Hello, my name is Albert Yorsher. I want to ask if we're talking about pure reference functional simulation or cycle accurate, structure accurate.
Yeah.
What is the accuracy? What are we talking about?
So for this level, and certainly for the high performance simulation, we're talking about instruction accurate simulation. It's programmer's view. Again, that interface on the simulator does mean you can start to do things like add timing annotation to the models. Obviously, if you're starting this early, you may not know what the exact cycle timing is. But we did a paper last year with Denso where they have very heavily added very detailed timing annotation to their model, and I think they're getting to within about 20% accuracy of the RTL, which is, it's always a trade-off of the more accurate it is, the slower the model is, and becomes a scaling problem. But the interfaces are there that you can do it.
Hi there. Following up on the chiplet question, what if the vendors you're working with only have encrypted RTL that you're purchasing?
So again, we are building functional models. We're not doing anything with the RTL. So long as the vendors can give us an architectural description of what we need to model, we can build a model of that system. In terms of constructing that, again, from a hardware point of view, that's outside of scope for what I'm talking about here. I'm not sure if that answers your question, but maybe I didn't understand it.
Synopsys has tools where you can also connect RTL as well as system
Yes.
models, right?
Yes. Yeah, so if you're talking about hybrid simulation there.
Yeah.
So yeah, we have the way to do that. I don't know enough about the RTL side of it though, but if you come over to the booth, I might be able to find a colleague who can help.
So a clarification, the golden models that you mentioned, those have to be developed by Synopsys. It's not something the vendor themselves can do. Is that correct?
They could if they wanted to. I mean, we can provide a processor development kit.
You can, okay.
Yeah. So if you don't want to work with us and you want to develop your own model, we can provide tooling to do that.
Okay, thank you.
I think we're pretty much out of time. Great to have the interaction, and if there's anything else, as I say, I'll be on the Synopsys booth, so please do come and chat.
Let's thank John one more time.